All right. So we're going to take a look at Chapter 6. Yesterday we took a look at 6.3 from the Nelson Physics textbook. Okay, so yesterday we were taking a look at how energy changes. Okay, and we came up with the following. We said Eg was at the bottom of the surface, big G, big M, M over RE. And this was, when we talk about it, when my rocket, for example, was on the surface of the Earth. No, she can't be inside Earth, like this. And so right here, my E total, my EG was negative G, big M, small m over RE. And then we said that as a rocket goes up to that point where R approaches infinity, your EG goes to 0. Your EG goes to 0. So this is what we said. And this was negative because we talked about it in terms of borrowed energy, correct? So yesterday we also talked about how if I want to make an object go from here to here, then there'll be work that was required, and that would be EG2 minus EG1. There will be your EG1, there will be your EG2. You talk about work, and of course your work is going to be positive. So this is what we talked about yesterday, just a recall of what we did yesterday. Okay. Okay. So today what we're going to do is we're going to talk about, I'm going to erase this, we're going to talk about the escape from the gravitational field. So escape from a gravitational field. Now when we're talking about escape, we're talking about how or what velocity I might need for my object to be able to leave the Earth's gravitational field. Okay, so if I am here on the surface of Earth and this is my potential well. Now potential well basically means the maximum gravitational force that exists that around Earth that will not allow me to leave, right? So I want to be able to imagine if I'm at the bottom of this well, I want to be able to go from here to here, and when I reach here, R is going to approach infinity, really far away from Earth, for example, and my EG at the top right here will be 0. This is what we're talking about. So the question is, if I want to escape this potential well, I want to leave Earth's gravitational field, go to Mars, go to Jupiter, go to whatever, what velocity do I need to have? What minimum velocity do I need to have? Do they, as I said yesterday, do they just fill up the gas tank and hope and pray that somehow we'll make it somewhere? Okay, the answer is no, of course not. We actually have a process as to how we come up with that. So this velocity that we're going to talk about right now, this is known as V escape from the surface. Okay, and to calculate it, we're going to start the following. We're going to say E total, which equals to EK plus EG, which equals to 0. Okay, so we're saying that the energy that is here at the bottom, by the time I get to the top, is all used up. So therefore it's 0. Okay, so bring the EK to the other side. So EK equals to negative EG. And you get half mv squared, which equals to negative G mm over RE. Now this is from the surface of the Earth. So we already know that my maximum energy is at the bottom right here. This is EG max. Okay. All right. So what we're going to do is bring everything up. So you get half mv squared, which equals to big G mm over RE. Okay. And then we're going to solve for v squared. So v squared, which equals to 2 times big G, big M, small m divided by small m times RE. So small m and small m cancel out, and you are left with V equals to the square root of 2 big G big M, which is mass of the Earth, divided by R of the Earth. This is V escape from Earth's surface. V escape from the Earth's surface. Now recall that when my object is in orbit, I have V circular. Now that V circular was V equals to the square root of big G mass of Earth times R, and this was radius of orbit from the center of Earth. Very similar formulas, but they do two different things. So please be aware that you understand when you are solving these questions. Yes. That's correct. At the surface. Yes. Okay. So we're saying all of the EG here will get used up and made into EK to go up to the top, which makes sense. Okay. So the question is, how much is this velocity? How much is this velocity? Well, since we have all the values, let's figure out what my Vmax is. My Vmax to be able to escape the Earth's potential well. And let's go take a look at it. Okay. So let's see, V equals to V escape equals to the square root of 2 times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by 6.38 times 10 to the 6 meters, and you get V escape, and the value is, yes, who can tell me what is it? Yeah? So 11,181 meters per second, which is how many kilometers per hour? So 40,255 kilometers per hour. Yeah. Now that explains why when you look at a space shuttle, we've got these massive tanks that are on the side of the space shuttle, because you need this much energy just to be able to escape the gravitational well. Yes. Of course it's being converted to kinetic energy. No, it's because it's been used using chemicals, right? Yeah. Are we good? Yes, so you're right in that it's not like when you have an object that's above a certain point on Earth and you throw it down and, you know, converts the EG into EK. Yeah, that's not what's happening here. True. Absolutely. Okay. So are we okay with this? Now this was your V escape. Yes. Yeah. Yeah. Okay. All right. So let's erase this. Okay. Are we okay with this? We're going to erase that. So if my object is in orbit, so imagine my object is in orbit right here. And if I want to escape from orbit, so imagine you make a spacecraft in space and then you fire off from here, like when you watched Interstellar or The Martian. You know, their spacecraft were in, they were already in space. So if I want to escape from this and I want to escape the potential well, what formula use? And the answer, you use exactly the same formula. V escape is still the square root of 2 big G big M. However, now this is going to be R instead of RE. Okay, yeah. You have to use the radius from there to the center of Earth. RE plus R altitude, which gives you R. Okay? All right. So another point that we're going to take a look at is as follows. So when an object is connected to Earth, what do I mean by connected? I mean I have my my potential well. As long as I don't reach this R approaching infinity point where I leave the Earth's gravitational pull, then if I'm anywhere here, from there to there, anywhere in here, I'm connected to Earth. I am bound to Earth. Okay? When I'm bound to Earth, and what energy do I have? So according to this chapter, we're saying that when you're bound to Earth, when you're in orbit, your E total is half EG. And you're probably wondering, what do you mean half EG? Well, don't worry, I'm going to explain to you how we got that. So if I'm bound to Earth, my E total equals to half EG. If I want to escape from my orbit, how much more energy do I need? Well, half EG again. Half plus half gives you E total at the bottom. Does that make sense? Half at the top there, plus half here, gives you E total at the bottom. So half EG when you are in orbit, another half EG to escape the potential well. Yeah? Yes. Yes. Okay? Are we good with this so far? So, I think we might have to do a couple of videos for this. Let's prove why this is half EG. And to do that, we're going to start out with the following. So we're going to say that we know that FC equals to FG, which is mv squared over r, which equals to big G m over r squared. If I bring the r up here, this becomes mv squared, which equals to big G m over r. So I'm going to use this relationship, and we know that E total equals to EK plus EG. So I know that this is half mv squared plus, or minus I should say, minus big G big M over R. Okay, so instead of this mv, I'm going to plug this in here. So this becomes half big G m over R minus big G m over R. Half minus 1 equals to negative half. So negative half EG. So when you are bound to Earth, it's half EG. Yeah? Say that again. I don't know. You tell me. What do you see? Yeah, well, what did I just do right here? This is mv squared, which equals to gmm over r. So what did I do? That's correct. I replace this mv squared, and I replace this. It's a relationship. I replace this with here. Well, what is half an apple minus a full apple? Half an apple